Okay, let's go back to the general definition of power. What's power? Power is how fast the work is done, how fast the energy is transferred, or how fast the energy is converted from one form to another form. All right, so speaking of power, it's how fast the energy gets converted from one form to another form. Now, electrical power is kind of interesting because there are two types of conversions that happen when it comes to electrical power. At one place, the current is going to be generated. At a different place, the current is going to be, at one place, the energy is going to be, power is going to be generated. At a different place, the power is going to be lost. And that's derivation power. All right, so we got two things. Power is going to be lost through a resistor, and the power is going to be generated at the battery. All right, so what's the meaning of power lost, and what's the meaning of power generated? Okay, power lost is how fast the electrical energy is converted into heat and or light. All right, it's and or light. So how fast the electrical energy gets converted into heat and or light. That's what it means. So the power lost is the energy is not being created or lost. What's happening is energy gets converted into heat or light and or light. So how fast energy gets converted into heat and or light. All right, so you got the power lost. It's happening within the resistor, and power is generated. That happens within the battery. So through the resistor, the power is lost, and through the battery, the power is generated. Okay, so we got 1 more minute to go. Notice that we got two different equations. For power lost, it's happening through the resistor, so you got the R symbol, and power generated is happening through the battery, so you have your V symbol. All right, so that's it. And there's also an intermediary formula that we will get to use, and that formula is almost a statement, summary statement. All right, so this is what happens inside the battery. This is what happens through the resistor, or you can use a generalized equation. This has the battery as well as the resistor in it. This is more of a summary statement. So there are three equations regarding power.
In 1987, Stephen Hayes was a young lineman, just 6 months away from completing his apprenticeship.
All right, so a couple of things about this guy.
This was a long...
He gets shocked. His bone marrow gets fried, gets infected. His arms are amputated as a result. He says that he was lucky that the current didn't get to his heart, and he says he was lucky that the current didn't get to his brain. My question was, how does he know that the current didn't get to his heart or the brain? Underlying assumption is if it gets to your heart, it will kill you immediately. And again, the underlying assumption is that if it gets to your brain, it's going to fry it immediately. Is that true? Those assumptions tend to be fairly commonsensical, and common sense is no substitute for education usually, guys. Those kind of assumptions usually don't hold water. So what does it take to kill someone using electricity? At this point, we're focusing on the fact that his bone marrow got fried, not the muscles. Muscles were okay. The bone marrow got fried. So the question is, why? I think one of you guys said that the bone marrow is probably not as good at conducting current. Muscles are, we know that the muscles are good conductors, because if the muscles were not good conductors, brain would not be able to communicate with the rest of the body. Through electrical signals, the brain communicates with the rest of the body. So the question is the bone marrow. Why did it get fried? It's the same amount of current. Same amount of current that hits the muscles as well as the bone marrow. If the bone marrow just completely, it just went boom. It just went.
Got more resistance.
All right, so the question is, go ahead. Yeah.
It's got more resistance, so then it generates heat.
All right, I'm going to give you 5 points. So does the bone marrow offer more resistance? Is that the reason why it heated up much more quickly than the muscles did? Okay, we've seen this before, and we will watch it again, and there's a reason for it. The only thing that I want you guys to pay attention to is the spawn. When this guy gets shocked, he will get shocked despite the fact that the charges will arc across without him touching the wire. All right, so notice that before he made contact with the wire, he does that. Okay, so physical contact is not a primary requirement. If there's a large enough voltage difference, the charges will jump the gap. Case in point, a case in point, a case in point. This happens maybe about 1 million times a minute here on Earth. That's called lightning. All right, the clouds don't need to touch the ground. If there's a large enough voltage or potential difference, the charges will arc through the gap. This guy, and he got zapped again. I just remember, if there's a large enough voltage difference or potential difference, charges will jump the gap. That's what a voltage or potential difference is, which means that the charges have enough energy to jump the gap. That's the meaning of the voltage difference.
It's kind of hard to figure out what's going
So what kills and what doesn't
on in this next video, but once you do, it is just terrifying, and I got to tell you, very graphic.
All right, guys, there's a warning here. It says graphic video. I've seen it a million times. The video itself is not graphic. You're not going to see the details. Or you're not going to see any faces, let's put it this way. But it's going to be nasty
Seen
nonetheless.
4
Okay, so let's talk about alternating current. So far, we're discussing this. Electric current is the title of the lecture. In reality, it's direct current and resistance. It should be direct current and resistance. All right,
It's
so
kind of hard.
what you're watching is what happens when there's alternating current involved. What the alternating current does is when it comes in contact with the body, because the muscles are electrical in nature, signals, the alternating current reverses direction about 60 times per second. So it paralyzes the muscles. It paralyzes the natural rhythm of the muscles. So if you're touching an alternating current source with your palm, automatically your palm is just going to grab it, and then it's going to get paralyzed around it. So you may not be able to let go. And that's exactly what's happening. So whatever this scaffold is, it's going up and it makes contact with one of the high voltage sources. And then everything is electrified. Now this is part of an alternating current.
Oh, I know what happened. I know what happened.
Watch this again. You see 3 of them on the left, 1 on the right. They're moving it, and then suddenly their bodies go
All right, notice that they are grabbing this bar with their hands, with their palms. So their palms actually paralyzed around it. So all 3 of them are part of the circuit at this point.
limp, yet their hands remain
All right, so one of the things that's going to happen is the body is a good conductor, but it doesn't matter how good of a conductor the body may be, it's still going to heat up because it offers a lot of resistance.
clenched on the bars.
And notice that this person is going to start to catch fire.
They accidentally pushed this scaffolding into some electrical wires above. Oh no, they're on fire!
Yeah, they're-
They start smoking, flames appear, and
Okay, somehow this guy was able to let go. Once again, you got a problem because it's on the ground. Notice that this entire scaffold is going to act like it's charged, point charge, so to speak. So at every single contact point is going to be at a different potential.
they fall to the
So the ground is already electrified at this point.
ground.
It's like being in an electric chair.
You think there's no way anybody gets up from this.
All right, so this guy is obviously started to smoke. This guy's
About
smoking. as well.
4.5 minutes in, watch this person here. You're seeing smoke, you're seeing flames, and then you see that person actually start to move.
All right, so he's moving, but once again, you have to remember that you have to deal with step potential right now. You notice that he's got one hand down, 1 foot is there, 1 foot is there. So you got all these 3 contact points, 3 different contact potentials that he has to
He
deal
gets
with.
up.
He gets up. All right, so when the legs are next to each other, he's going to be fine. But when he steps forward like that, once again, boom, the current is going to
Tries to get out of there, hits into the scaffolding again,
The body paralyzes
falls to
briefly.
the ground, and then eventually is able to regain consciousness and get out of there. Details from this are somewhat sketchy. We've translated a number of news articles from China. We've been able to learn that 2 of these painters were killed. 2 of the others, of course,
Evidently, there are 4 people, so 2 of them died, 2 of them survived. Surprisingly, 2 of them actually survived.
very injured, one of whom the guy who walked away. Apparently, the lines that they ran into, 10,000 volts
10,000
of
volts.
electricity. So hot that even the plastic wheels on the bottom of this scaffolding melted, and the scaffolding was stuck to the ground.
So alternating current is what causes problems usually. You become part of a circuit. So what does it take to kill someone using current? Number 1, it needs to be alternating current for the obvious reason. Because when it gets to the heart, it just messes up the heart's electrical rhythm. That was the initial thought that they had when they were designing the first electric chair. All right, so we'll get back to the question.
This little light burns all day.
So question number 1, how does electricity generate light? And we talked about this particular light bulb. It's been around over a century. So the question is, why did the company go out of business? The company went out of business because this light bulb was not generating enough light. So the question is, why not? Okay, part of the reason is because they were using a carbon filament. So why did they make the carbon filament so long? And why is it so thick? What's the idea behind making it long? What's the advantage that they were trying to gain by making it long? Any suggestions at this point? Just jump in if you have a suggestion. If not,
More resistance.
okay, so by making it longer, so it offers you more resistance, right? So if it offers you more resistance, how does that help? Yours have 5 points for that one. What's the advantage of having more resistance? All right, okay, so I'm gonna give you guys 5 points, despite the fact that it sounded kind of weird. All right, larger the resistance is, what's the benefit of having something with large resistance?
It ends up being a lot brighter because more heat is trapped, and then the waste is brought on as light.
I'm gonna give it 5 points. We'll get back to it shortly. Clean that up. Come up with a little bit more formal way of looking at it. Okay, so peeing on the 3rd round.
It's late. You've had a few drinks.
Would you get shocked by peeing on something electrified?
There's no
Would you get electrocuted by peeing on the 3rd round?
train expected. Nature's calling. What?
All right, so we've ran the numbers. I think it's 65 milliamps of current. That would be the amount of current going up the urine stream. So the question is 65 milliamps of current. Would that be large enough to kill? The short answer is yeah, it would be large enough to give you a heart attack if that's the amount of current that gets to the heart. All right, so when they set it up, they came up with a relay, which is going to act like the heart within the dummy, except they set it up to 65 milliamps to trigger the relay. So do you think that the current value ever going to get to 65 milliamps by the time it gets to the relay? Yes or no?
No.
The answer to that question is no. So what are the chances that this experiment will ever succeed? It's set up to fail, and it's not going to work, and they're not going to know why, and it's going to cause a lot of confusion. And they will conclude that there's absolutely no way you could get shocked or electrocuted by pissing on the third ground. In fact, 2 people, I don't know if they must be big fans of the show like myself, end up getting themselves killed by pissing on the third ground. One guy from Chicago, the other guy is from Brooklyn, New York, Brooklyn. And both of them, they didn't stand the chance. They probably thought that it would be funny to piss on the third round. Guess what? Joke was on it. So they did not survive. So the question is, why did the experiment go so badly wrong? Part of the reason, these guys are not physicists. They're not engineers. They're special effects artists. And when it comes to electricity and magnetism, a lot of the times their conclusions are way off, as you will discover this semester. So I love the show for all the wrong reasons, because it gives me great opportunities to discuss this. All right, so speaking of step 3. If there is a high power line on the ground, all right, as you well know, don't walk towards it. We discussed that.
Yeah, they're not as quick.
And I'm showing you this little video clip just to illustrate how dangerous it is. The ground is literally going to heat up. I don't know where the power line is, but the ground is electrified. These guys on the other side of the fence, they think that they're actually safe. Notice what happened. The current travels immediately after where they are.
There, that might have did it. Nope.